Hi guys. Okay, so welcome back, and we're gonna do this problem again regarding mechanics of material. In this case, we have this rod, okay, that has two sections. In this case, there is the cross-section area, which is A1, and we have another area here, which is A2. So the cross-section area is different, and this rod is being, pulled apart by these forces, okay? So if I don't have, for example, I always ask myself, maybe this is a silly question for you, but for me, when I was doing this stuff, I was saying, well, what about 200 here and 100 here? Why they need to be the same? And the basic answer is because otherwise it's moving. And in this type of problem, mechanics of material, we are not looking at dynamics or movement. That's not important. What we are looking for is here something to calculate it. So in this case, we're going to try to get the normal forces. So let's just get the normal stresses. And these normal stresses are calculated by the load, the axial load divided by the cross-section area. So cross-section area for each one of these sections are known. So we got them. And then we have this information here. So this is the elasticity modulus. This elasticity modulus, it's a property of materials that tell us, well, okay, you know what? I'm gonna produce this normal stress. Let me see how this thing will strain. So how much deformates is like an idea of deformation. Okay, it's gonna happen. Well, this one is a property of material. Will tell me if you apply, I don't know, 1,000. Maybe this guy will be high or low depending on this property of material. Okay, so that's what we are having here for this problem. I'm gonna erase everything so you can say that that this thing's a little bit more clear. But the basic idea is that do the distribution. The distribution means that you need to do, okay, so what about the normal stresses when I begin here, say x equals to 0 till this point, okay? So how this normal stress will look like, and also the same thing by the strain. Okay, so the strain is just this epsilon, and you can also calculate it from here, and it's just the normal stress divided by the elasticity models. So that's what they are asking us. I'm not going to talk about a lot of theoretical part. It's just to do this problem, and it's actually basically simple, a simple one to do. Okay, so let's just start with this part. So what I'm going to do is I'm going to break apart this section of the rod, and that will give me, so if I'm going to move over here, and that says, well, you know what, you have your 200 kilonewtons going to the left, then you have your section 1. Remember, this has its A1, and then I break it apart. So here, this thing should be filling inside of it this 200 kilonewton, okay? So if it's filling 200 kilonewtons, therefore, from here to till this section ends, so till this section ends, it seems that the normal stress will be the same one, because now I can calculate sigma 1, let me just put it here like that, and this one's going to be this P1 divided by the area 1, and I have everything I need, okay? This is not very complicated. The complicated part is to understand the theoretical part, but to do the problems, once you have data, it's already there. So I'm going to put 200 kilonewtons here, kilonewton here, and they are already giving me this in square millimeters, but I'm going to put it like this, 2 to the -6, which is same thing, but in square meters. You can keep it in square millimeters, no problem. Okay, but with this, the answer that I have for this fella is 133.3333, but megapascals, okay? So please remember, if you're gonna do kilonewtons and then divide it by square meters, this thing will give you kilopascals. So what I did is I just divided by 1,000 in my mind in order to get this one over here in megapascals. That's not everything. So I'm gonna now calculate the strain, and the strain is just the relationship between the normal stress divided by this property of material, the elasticity modulus, and this one is going to be it's going to be equal to, well, 133.333 megapascals divided by, take a look at this number. So this number is 70,000 megapascals. So 70,000 megapascals Okay, you can put this one also in gigapascals to see what happens. But okay, so this number is a small number, 1.904, 10 to the minus 3. It doesn't have units. Okay, so that's the strain. That's what it is. Okay, the strain is length divided by another length. So it's a relationship, a ratio of lengths. Okay. Okay, so in this case, this is the strain, and therefore I have everything. So from here to there, to this point, okay, so I'm going to put it this line. So all the way down here, what I have here is that I have my 1.33, 1.33. This guy is going to be in megapascals. Meanwhile, this one over here, I'm going to put it 10 to the minus 3. So I don't need to put a lot of numbers. So this one is going to be, let me just put it here, 1.9047, and this one is going to be constant till I get to the other part of the rod, and this one is going to be constant till I get to the other part of the rod. So that's what a distribution is. Okay, so how this thing can be changing or maybe be changing along the length of the road. Okay, that's what's happening. Okay, so it seems that if I can do this again here and I can do this again here, and the answer is going to be the same one all the time. Therefore, that's why it doesn't change the normal stress and neither the strain. Now, let's just go with the other part. So the other part is this one here, and I'm going to do this one. I'm going to do the other part. And this thing, I'm going to take the right part of that. So it's this 200 kilonewton, okay? And then I'm going to break it to my left. You can do it. It doesn't really matter where you break it. So this should be 200 kilonewtons here. Otherwise, this thing will move, okay? So for here, you will get that sigma 2, which is the normal stress at 2, is going to be like this. Therefore, you still have your 200 kilonewton, and everything's going to be divided by, so in this case, my area is 1,000 square millimeters. So 1,000, 10 to the minus 6 square meters. Okay, and now with this, what I would have here is that my number is 200 megapascals. I'm just saving you a little bit of unit conversion. Let's just go with the strain at 2. So the strain at 2 is going to be equal to this sigma 2 divided by the elasticity. So the elasticity in this case is 200 gigapascals. Let's just put it like this. So I'm going to do 200 to the 10 to the 3 in order to get, I don't know, that's wrong. Yeah, it's not that very wrong. Now it's correct. I'm going to put gigapascals up there, and these are 200 gigapascals down there. So in this case, what I have here is 1.110 to the minus 3. Okay, so what I have there is that. That's the strain, okay? So that's kind of the strain there. That's it. So now the only thing that I need to do here is from here, I can begin here to this place, or maybe you can start here. You can say, well, you know what, there's gonna be a jump there, and in this case it will give me this place, which is sorry, I think I think I put these numbers wrong. So this one is gonna be, I think it was this color, I don't remember. So 133.3 megapascals. And in this case, for the green one or the right part of the rod, it's gonna be, so 200 megapascals. So it's a little bit higher than the left part. So you have more normal stress there. And in this case, let's just look at the strain, and the strain is smaller. So in this case, you have more strain, and in this case, you have less one. Okay, so I just put a bit lower than that, 2, and this one is gonna be 1.1.0. Okay, so 10 to the minus 3. No, dimensionless. This one doesn't have any units. Okay, and that would be the distribution of both guys. Both guys mean normal stress and strain along this rod. Okay, so I will see you later.